Start the video.
Okay. I'm going to make sure that works. Okay, we're good.
Good afternoon, everybody. We're just setting up a few technical details before we start, so we're going to be presenting in about 2 minutes from now.
Don't forget your coffee.
Before we begin and introduce, I want to just remind everyone that we have everybody on mute for now. And at the end of the presentations, we're going to open up questions to everybody, either through chat or through using your microphone. And you could either raise your hand or just unmute yourself, and we will have an open discussion and questions after the presentation.
Yep.
Where's the camera?
Right over there. I'm going to go to my office, make sure that we have no audio issues.
But for us, it's afternoon, so good afternoon, everyone. I want to welcome everyone to our the LEHIGH seminar series. This is actually organized and hosted by our seminar facility here. Our facility is associated real-time multi-directional hybrid simulation. Today's seminar is entitled Solutions for Mesoscale Monitoring. It's going to be presented by Dr. Austin Downey. He's a assistant professor in mechanical engineering from the University of South Carolina. A little bit about his background. His area of interest in terms of research includes resiliency of mesoscale structures, both man-made and natural events or hazards, if you wish, through the real-time monitoring, modeling, and adaptive control of structures. He has numerous publications, including 20 journal papers so far. His area of special in terms of his PhD is in engineering mechanics and wind energy, and he received his PhD in that topic from the University of Iowa State. Okay, so with that, I'll welcome Austin.
Well, thank you very much, Jim. As Jim said, my name is Austin Downey. I'm currently at the University of South Carolina, just started there in the fall in the Department of Mechanical Engineering, also in the Department of Civil Engineering. So today we're going to talk about some of the work that we've been doing at the University of South Carolina, and some of this continues my PhD work from Iowa State University. At the end, we'll talk briefly about some multifunctional materials for self-sensing cementitious materials, and that's been done with the University of Perugia in Italy, kind of as the main collaborator there. Real quick overview of what we're going to discuss today, an objective, why is it that we are spending so much of our productive life on this topic, and then we'll talk about the SEC-based sensing skin, which is a technology that we've developed at Iowa State and now at the University of South Carolina, an algorithm specifically designed for that, to look at incipient damage detection, and then some self-sensing cementitious materials, and then finally we'll look at a quick review. So the objective here that we're working towards is to enable life cycle management of mesoscale structural systems through the use of dense sensor networks. So a mesoscale system is just going to be a large structural system, so airplanes, wind turbines, bridges, things of that class. And so data extracted from a dense sensor network, we're just going to abbreviate this as a DSN through the course of this presentation, can enable condition-based maintenance, smarter load management, so we can take our structures and use them how would be best suited for the structure's health, prognostics and health management, but most importantly, reduced operations and maintenance costs, right? So a lot of this is being pitched towards the view of owners and operators of structures, and if we're not able to reduce their operations and maintenance costs, then there's really no interest in this. So with all that in mind, what do we need in an ideal dense sensor network? First and foremost, it needs to be cost effective, right? We cannot take a structure like the Charlie Weston Bridge here in Northeast Iowa and try to sell them $1 million monitoring scheme. So these need to be cost effective for the situations we're looking at. It needs to be able to provide global coverage, but also needs to be able to distinguish localized from global damage. It needs to be both robust and durable in terms of how long the sensor can last and what kind of operations it can last through, and provide the owner operator with actionable data, right? So again, this bottom one is probably the most important. If we're not giving the owners and operators something to do with their data, it's not a lot of use. So when we talk about actionable data, what does this actually mean in terms of life cycle management? So if we start down here at the bottom left and we have a structural component, and we have some real-time operation monitoring, this dense sensor networks is what we are interested in here in the presentation today. That's this top blue box. And there's 2 sensing technologies here, but there could be millions more. Typically from dense sensor networks, we'll look at a feature extraction and get us down to some feature processing, some prognostics, some condition-based maintenance. But again, all of this has to cycle back into giving the owners and operators some sort of actionable data, something that they can actually take to their structure to reduce their operations and maintenance costs. How does this fit into the terms of, what we typically consider as maintenance schemes? In terms of complexity on our vertical axis here and then benefits on our right axis, we can start with breakdown maintenance in the bottom left corner. We're just going to repair things when they're broken. The next step up from that would be schedule maintenance. So airplanes have components that have to be inspected every 3,000 hours or 500 hours of flight and engine components. Beyond that, we can start to do some preventative maintenance. This is when you start to look at NDE techniques, right? Determining how a component failed, determining why a component failed, trying to see if that component needs to be failed. But what we really want to push is condition-based maintenance here, right? And to get to condition-based maintenance, we need information that's looking forward into the future. So for this, we really need real-time fault reporting, and this is where the idea of dense sensor networks comes in. This is the last kind of slide I have on this need for actionable data, and I took this picture myself. This is a wind turbine blade south of Kotzebue, Alaska. So that's 33 miles north of the Arctic Circle. There's damage on this blade. We know where the damage is. Typically we're trying to look at damage location, quantification. We know relatively how big this damage is, but that blade operator had repaired that damage once, and then the repair failed. And what they were looking for is some sort of actionable data. Someone who would come in and actually give them some information about how this blade was going to act into the future. And so what we're trying to develop are sensing technologies that can track the degradation and give us some prognostics into the future. So now that we have a bit of an idea of why it is that we're working on things, we can look at some technologies. So first we'll talk about an SEC-based sensing skin. This is a fully integrated sensing skin. So it comprises small individual sensors that we manufacture. And our goal would be to integrate these into large sheets that have all of your controls, your wireless communication, your power, everything integrated into a whole sheet. Our goal would be that this would be a solid polyamide sheet that you could roll up either as an OEM application or in like a maintenance term, pop off the end of a tube, put some epoxy on a structure and just roll out one large sheet and you're done, walk away. When we start to develop new sensors for structural health monitoring, the question becomes why. There's lots of sensors we have. And so we want to kind of compare this to what's the state of the art in the field. We want a sensor that's inexpensive. So working across the top row, a sensor that's scalable with simple implementation, compact data acquisition, robust, and can distinguish local from global damage. And obviously not picking on any other sensing technology, but everyone kind of has its own benefits and drawbacks, right? So a typical resistive strain gauges, like these are inexpensive, but they're not very scalable. Covering large structures gets very complicated. They do have compact data acquisition. They can distinguish local from global damage, but they're not simple to implement and not robust. You can kind of work your way down through the list. We won't spend too long, but we feel that the dense sensor network we're developing could easily do all of these and offer some real benefits. So a little bit more about the actual sensor. This here is the SEC, the soft elastomeric capacitor. And these can be made in any size. They're cheap and flexible. They are made using simple equipment. It's just a dielectric. Let's see if I can. So it's a dielectric here that we drop cast, and then we paint a conductive layer on each side. And that conductive layer on each side forms a capacitor with a very simple electromechanical model. So we can get a change in capacitance is a function of our relative static permittivity and the dielectric constant multiplied by the area over the height. And so a change in area and a change in height when we stretch the capacitor will give us a change in capacitance. And it's an additive strain, epsilon x plus epsilon y, with a gauge factor of about 2. But the low cost allows us to cover very large structures. It's a very durable sensor. You can cut holes out of it, right? And the sensor itself will still work. So here we have a sensor that a small circle was cut out of, and we still have a capacitive value for the small circle and then a capacitive value for the rest of the sensor. There's very few other technologies you can do that with. You can't cut a fiber optics strand in half and still have it working. In terms of vandalism, interested in using this for civil structures. So what happens if a teenager cuts it with a knife? So here's some knife cuts on a sensor. And you can see that even after the cuts, the sensor still works. We do have a shift in the baseline, but the sensor itself is still working just fine. Now, in terms of weatherability, again, we're interested in long-term monitoring of structures. So we did some accelerated weathering with our collaborators at the University of Perugia. And so this is 30 days of accelerated weathering, 24 hours of constant cycles of intensive UV, humidity, thermal, just every 2 hours switching in between. And after 30 days of accelerated weathering, the sensor itself held out just fine. There's a little bit of degradation along the edge of the dielectric, which is weaker, but most of that was from removing it from the plates. Here's some mechanical testing values. We tested the dielectric without any carbon black protective, and those do degrade, and that's why you lose these colors as we move over. But these pink, brown, and teal, or pink, brown, and purple are the ones that are actual SECs, and those were able to hold their strain to rupture all the way to the end. Just another way to look at that is the stress that it took to rupture. Regardless of the aging, they're pretty constant. And then the Young's modulus, right? So any of the actual SECs, which are the 3 that made it all the way out to 30 days, have a very long, stable lifetime. So this is helpful in giving us some information on how long these are going to last in the field. So on the orders of years is without an issue. Another thing we wanted to look at was chemical degradation. Are we losing mass as these are aging? And even the ones that we had all the way through, so we have a residual mass that's pretty constant, right? So we don't have a lot of chemical reactions going on in the setup. But the most important part is how do they act as a sensor once they've gone through this accelerated aging? So here we have a sensor. You'll notice it's actually cut in half because we had to take some of these samples out of it. But even being cut in half, we can still use it as a normal sensor, and we are able to track the additive strain just fine. So in a civil application, what is it that we're actually looking to do? One of the things that we're interested in doing with the DOT is fatigue crack detection and fatigue crack monitoring. So this is a several-year project that just finished up. And here we have a dense sensor network of SECs deployed on a test coupon and a compact fatigue test. And we have 4 SECs, and we have the data from the 4 SECs. And you can see that as the crack grows under SEC number 1, we get a large increase in our measured capacitance for SEC number 1. Pretty simple to understand, right? We have a opening of a crack, we have a change in deformation, and that's going to show up as a change in capacitance. Sensor works just fine for that. What if we're interested in a more complex cracking situation where we don't know where the cracks are going to form? We can solve this with the use of a dense sensor network. So this was again at the University of Perugia on the back of a concrete plate. And so we've got 20 SECs on the back. And when we impact it with the hammer, so this hammer on the front just kind of repetitively falls into the concrete plate. When we impact it with the hammer, what we get are anytime that a crack goes through an SEC, we're able to detect it quite clearly. However, when we have cracks that form around SECs, which you can see happens quite readily here, we have more challenges. And this would have to be solved through a model-based approach, right? Looking at actual strain maps. But the other interesting thing is we can make these SECs in any shape we want, and they're incredibly elastic. Right, so here we have 3 SECs on a steel wire reinforced concrete beam, and you can see that as the beam opens, right, we get a lot of opening here. We can track all 3 displacements from 3 different SECs, right, 1, 2, and 3. Oh, you don't see it?
You only see your, sorry.
Oh,
Yeah, let's do that again, sorry.
do we have to do that for every video?
No, sorry, we're gonna just do your whole desktop. Mm-hmm.
Well, we can watch it again. It's super exciting.
Nobody got to see it.
It's riveting. It's okay. Try it again. Okay. You see it now, Tommy?
Still don't see it. I'm sorry.
It's fine.
Stop the share.
We can tilt the camera around.
We should share your screen. Okay. Yeah. Try it again.
Okay. So should I close out of it and open it?
No, you're okay.
Is it working?
I'm gonna double check. Sorry. Just continue.
Okay. So if you can see the video, what you'll see is we have these 3 SECs mounted on the beam itself. And as the beam opens, right, we can track the opening using each one of the SECs. So these are highly elastic, and this gives us a flexibility that other sensors don't, right? Because we can use this over large opening and cracks, around corners, around welds. And the flexibility allows us to install them anywhere. So another thing that we can do that other sensors have issues with is full field strain measurements.
So of course you could do this with like digital image correlation, but that's hard in a monitoring situation. So at Iowa State University, we have a wind tunnel. And what we did is we built a model wind turbine blade, right? Introduced some buffeting to it. We have this fiberglass substrate on the side. And then inside of that, we put 12 SECs, right? And so these are much smaller SECs, but they're still the same thing. And here's the wind in real time. So this is the blade operating in real time. Other videos, there it goes. Here's the wind blade kind of buffeting back and forth in real time. And then what we can do is take our SEC measurements and rebuild dynamic strain maps. So here we are slowed down, and we have epsilon x and epsilon y. Again, we measure the additive of the two, and we use an algorithm that we developed as part of my PhD to decompose them, but we haven't really discussed that here. But what you'll notice is from the x and the y is you get tension and compression right next to each other, and this shows that the turbine blade is actually, there's a moment, there's a torque in it, and you can see that twisting in the tip of the blade if you watch, right? You can see the tip of the blade twisting, and the SECs are able to pick up that torsion in the blade through a full field strain map. So they work real well for large scale structures, for monitoring very easy to detect cracks. But again, we're interested in doing developing these for life cycle management. To do that, we really need to get some prognostics data. So what about the smaller cracks, right? So here we're going to develop an algorithm, or talk about an algorithm we developed for incipient damage detection. And so why focus on incipient damage, right? So direct monitoring of cracks is relatively easy, right? We put a few sensors down, we have a crack, it forms, we're good. Indirect monitoring of internal damage is definitely more challenging, right? So it's undetectable through traditional threshold algorithms. We're not just going to see a clear step in incipient damage. Better prognostic capabilities if early stage damage is tracked, right? So we can understand how this damage is going to grow the sooner we track it. Some of the things that we really want to be able to do are localize damage within the sensing skin, right? And we really want to do this without a black box algorithm. So nothing wrong with, a lot of like deep neural networks, but we want something that we can give to an owner or an operator that's physics-based, that we say, hey, this is how we see it, this is why we see it, and helps them believe it. It's all about trying to get actionable data back to them, instead of giving them a black box and saying, the machine has shown us that we need to do this. And then the follow-up question is always answered with, I don't know how, but it did. So spatial interpolation, I'm going to give a quick review of this just because it's an important part of the algorithm that we developed. We're going to talk about kriging here. Other spatial interpolation methods could have been used, but we went with kriging for a reason that's pretty simple to see once we get there. So in this method, we have our real data, which is our black dashed line, right? And so we just have the system over X, just a numerical system. We only take our values at the red dots, which is our input data. And then our predicted values that we get from kriging are this thin red line, right? So here we kind of overestimate, here we underestimate, but we always go through every dot, and that's important to notice that we're exact. And then we have these confidence intervals that kriging gives us, right? So kriging gives us these confidence intervals, and they're distributed about the predicted values. And so how do we get these predicted values, and how do we get these confidence intervals? Real quick, there's a couple different forms of kriging. There's simple kriging. We won't really discuss this. It's more of a mathematical proof of concept. But we do have a state. We have Z is the predicted value at X. For simple kriging, we have a value mu that's constant over the entire system and known. And then we have an error value. So not a lot of help here because we don't know our mean value. Ordinary kriging says it's just the next step in the line where now we can solve for u, but again, our mu is constant over the whole system, so not of an interest when we're looking at strain maps over spatial deprivations. So we're going to use universal kriging, and this is a predicted value z at a location x, and it gives us a mu, our mean value at location x, plus our error at location x, right? So this is also called kriging with external drift or regression kriging. Different people in different fields particularly use different terms. We won't go too deep into the math here, but what's important to know is that it can all be done with linear algebra once you have a variogram detected. And so we are building this model here, which is our model Z is a function of our mean value and our error at each location X. This can be done through matrix algebra. Q is a vector of predictors at our location X0, and X0 is the location where we have interest in. So beta can be solved for, using generalized least squares, but for this beta, we need our C, our covariance matrix, which is a matrix of residuals. This is not a matrix that we have. It's not a matrix that we can measure. It's a matrix that we have to build. So to build this, we're going to use a variogram model, and we chose a power variogram model just because it's asymptotic and it's easy to model and very stable. The important thing to notice is that it's stepwise. So if our distance between the data point that we have and the data point we want to estimate is 0, so if we're right on top of the data point that we know, our covariance is 0. And this gives us an exact solution. And then anything where our distance is greater than 0, we start to use this power distribution equation, right? So this gives us into two equations now. For each value in the field, we have an estimated value at our location Z, and then we have our error value at our location Z, or our standard deviation. And we can use these in a algorithm as we move forward. It's a more compact way to write it, but it doesn't matter too much. So again, back to our plot that we looked at before. Now at any location, we have our mu value. So let's say we want to go about 55. Our mu value is going to be right here at about 75, and our variance is going to be the distance of our confidence interval. So we solve for the mean and the variance at each location. Solutions are exact, and the predictions equal the training data at the training locations. We need a variogram model, and so here we use the power variogram model. We also need a drift term equation, and we just use the linear drift for simplicity and ease of code. So now we want to look at how can we start to use this algorithm to extract some more information from our system. Again, we're not able to actually see the damage in terms of signal, so we have to use a statistics-based approach. And for that, we're going to use a Kullback-Leibler divergence, and this is the measure of the dissimilarity between two probabilities. So we have a probability P and a probability Q. And we're going to take the convolution of the two, right, and then take the area under our convolution curves. And so this gives us a quantifiable probability between two, quantifiable dissimilarity between two probabilities. This has been used before for incipient fault detection, so it's a good place to start. And it's computationally simple, except for when we have this in a continuous integral, which is very difficult to do. But we can recall that kriging gives us our mu and our standard deviation for each value. So if we put these into normal distributions, we now have a very simple mathematical expression that we can get for our dissimilarity. And all we need to know is our average value of our standard deviation, sorry, our average value, our mean value, and our standard deviation for our two probabilities. And that's very easy to obtain. So now that we kind of have some information on how kriging works and how Kullback-Leibler divergence works, we can build a very simple algorithm that's very easy and very quick computationally to solve. So on the top left, we're going to go, we're going to collect our SEC signals. So here we have 100 sensors on a cantilever beam, and we'll show that in a little bit. Geometry fusion, which is another algorithm we developed that isn't needed, but is a way to get better accuracy strain maps. And then we're going to develop a full field map of P, right? And this is just what we get from our SEC data. And so we get one map for our entire sensing skin. And then we're going to develop N full field maps of Q. And so Q is our other probability. And so since we have 100 sensors, we're going to get 100 maps, where each map is the spatial map with one sensor removed. We can do our Kullback-Leibler divergence between the two maps then. And so we're going to end up with 100 different maps, right, that look like this, which is the KLV between P and Q. Here we have a damage, which is this little black line. And what you can see is as we move the sensor that we remove from the data set, closer to the damage, we get a very large Kullback-Leibler divergence, right? But when the sensor itself is farther away from the damage, we have a much smaller Kullback-Leibler divergence. We end up then with 100 different KLDs, and we just stack them on top of each other, take the L1 norm, and then we end up with a spatial damage index. So if we want to simulate this real quick on a computational model, we've got a cantilever concrete beam here that's loaded to the tip, and we have 3 damage cases. Damage case 1 was selected to be in the middle of an SEC, kind of in an area of high strain. Damage case 2 was selected to be in between 2 SECs to see how well that would work. And then damage case 3 was selected to be towards the center line of the beam where the strain would be a little bit lower. The neutral axis was a little bit farther down, but it's relatively close. So just some different test cases of increasing damage. We just increased damage by reducing the stiffness. And so what we end up here is a strain maps are in the left column. So this is what's actually measured. And this little square here is the damage. The spatial damage index, which is the algorithm we just discussed, is in this column. And then Laplace and Gaussian gradients, right, which are commonly used damage detection algorithms for spatial image reconstruction. And what you'll see is that the SDI does quite well at detecting damage, right? So on low levels of damage, it'll detect dissimilarities kind of up here around the corner. Obviously, nothing is detected in Laplace and Gaussian. And then the SEC, you can't really see on the actual strain map, you can't see the damage at all. Once you get to the next level, this SDI algorithm correctly localizes the damage, but you can't see the damage here in the strain map. And then Laplace and the Gaussian don't detect it at all. And then in the damage case 10, you might be able to see some damage there. It's a little debatable. I definitely wouldn't stake anything on it. But the SDI algorithm clearly picks up the damage, and Laplace doesn't pick it up. It picks up damage around it, but the Gaussian starts to kind of pick up some damage in that location. So the SDI is able to pick up damage before these other 2 algorithms. These are just moving the damage location. So here we're going to move the damage location to the right. Again, same situation. We have a damage location. We have a damage situation where it's relatively small and we can't pick it up. We start to pick it up and then we can pick it up clearly. And then we're always outperforming the Laplace transformation, and then the Gaussian we're outperforming quite well. And then here's the 3rd damage case, closer to the middle. Again, similar situations. The Gaussian starts to pick something up, but not very clearly. Really kind of picks up areas, while the SDI algorithm starts to really pick things up in an incipient damage location. So those are some numerical studies on the SEC algorithm, and we can definitely talk more about that. There's much more work. But something that actually is pretty interesting and is in a much earlier stage is the self-sensing cementitious materials. And this has been work that has been done over 3 trips that I made to the University of Perugia in central Italy with my great collaborators there. And so they've been working on self-sensing cementitious materials now for a couple of years. And so here we have a scanning electron microscope of multi-walled carbon nanotubes. And these are actually carbon nanotubes. And then we'll suspend these in concrete. And so here you can see a single nanotube kind of suspended in the concrete. The trick here from a manufacturing and scalability issue is how do you mix your materials and get them suspended in water and get them to mix neatly into the concrete. But once you get them into the concrete, you can create materials that are capable of monitoring their own transient, dynamic and transient loads quite easily, right? So here we have a material mounted in a compressive cylinder. We are cycling loads to it, and then we can measure change in resistance, right? That lines up quite well. We can do the same thing with transient damage. So here we have a beam. We cast this beam in the summer of 2017. And then here, about 8 months later, we did a transient load once the concrete had dried. You impact it with the hammer, and you can detect the vibrations in the beam with the concrete sample itself embedded in. While those are actually very interesting, I'm interested in long-term modeling, right? So how do we develop this for a long-term approach? And the key challenge here has actually been that this material drifts. So if you start to take a measurement of it with time, this is what you actually see, this kind of constant upward drift. And a lot of papers will just say we will leave it measuring for a couple of hours until we get to a constant place, but not really good enough if we want to understand this drift. So there's been some expertise with trying to model this. Some people have had more luck than others. Proposed solutions to get around this drift, has been delaying measurements, AC measurement approaches, which can and can't work, but also make multi-point samples hard and are much more expensive. Electromechanical modeling, which is a good attempt, certainly, and then just comparing it to a control sample. So you have a control sample and another sample, but what happens if you have an issue with your control sample, or your control sample kind of comes out of phase? So as a simple way to alleviate this issue, we just hooked up a biphasic DC function generator and created a biphasic DC signal, and then developed a measurement approach around that. So we're going to continuously charge and discharge this material, both positive and negative. This blue line here is what you get with a DC approach, right? So you have this rises up and continues to raise, and then these horizontal lines that are kind of squiggly are the different frequencies of the DC approaches, right? It doesn't matter what frequency we choose, we get a nice horizontal line, but we get a little bit more noise. So typically we're just going to use a 1 Hertz signal for the remainder of this work, because we're not super worried about the noise. What we want is stability, right? And so our first attempt at kind of solving this was to develop a resistor mesh model. This is just a model of resistors that we solve for numerically. We do this in SPICE, which is an open circuit, an open source circuit simulator from Berkeley. And we can do this kind of repetitively to solve for a solution. So so here what we have is this resistor mesh model that we will build for a sample. Here we have a sample that we're going to measure the voltage at several locations. And then here we have a actual results up in the corner. And so the data line is what we get with what we're actually measuring. And then by adjusting the value of the damage around our cracks, right? So we have 2 cracks here, 1 and 2. We can adjust our data to match that pretty well. And so here we have adding crack depths to it, and then with the increase in crack depth. So we're just sawing through it, and our model is able to track it. And that video is not gonna work. Okay. But then we wanted a much larger beam. And so here we have a much larger beam. And this whole beam is filled with multi-walled carbon nanotubes. And it's simply supported. And then we're going to apply a load down the center. And what we get is we can track the strain kind of throughout the beam at different sections. We can track that quite well. And then at an applied load of about 1.7 kilonewtons here, we have an audible crack that forms in the beam, right? And so this drop here is a functionality of that crack opening. This crack was already there. It was a surface crack, and inside the beam, that crack actually opened up a little bit more. But there's no real way to see it visually on the surface, right? The crack was already there, but we can model this internally, and we can get a model that matches this data quite well, and helps to reinforce the idea that we can track damage. But these were done, sorry, it keeps moving. All of this was done by moving these resistors manually and kind of setting resistor values to recreate that crack. But we want to do this automatically. And so we went back and kind of thought about this again, and how can we automatically place damage resistors into a mesh. So we need a data set that continuously grows, and to do that, we took this concrete plate. So this is a 0.5 meter by 0.5 meter concrete plate filled with multi-walled carbon nanotubes, and we repeatedly impacted the plate. Here's again and again and again. Here's kind of our experimental setup, and then here's our resistor mesh model. So what we're going to do, instead of trying to place damaged resistors, we built an automated placement algorithm, and this is just sequential Monte Carlo. It's 11 lines of code, and we're going to start with an initial guess. We're going to try a lot of guesses from a uniform distribution, pick the best one, and drop it down generation after generation after generation. So the advantages of this is that it's very easy to program, and it's very easy to parallelize. So actually, the code itself runs quickly if you can get it on a machine with lots of cores, which we were able to do at Iowa State. Some of the drawbacks, though, is it's relatively slow and that has a large search area. It's not very efficient, and it focuses on the largest damage first, right? So if you have a large damage in your structure, it's going to concentrate all of its ability on that large structure and then slowly move through. So here we can see the pristine case of our plate. This is what our algorithm gives us in change in resistivity. And then after we impact it, we have 3 spots on the plate where actually we lost a little bit of concrete. And so we lost conductivity here, here, and then on the back, right? And the benefit of this method is it doesn't matter if it's on the front or the back, it can pick this up. And we were able to find kind of these 3 losses of material. If we subtract one from the other, we get a much clearer look, right? So a challenge of this is that when we have situations where we have a crack that opens and closes, you're not going to see that because your crack is going to reclose and you're going to gain a lot of your conductivity. But anywhere where we have spalling or a loss of material, it's pretty easy to see. Again, we're kind of interested in developing this for prognostic reasons. And so if we take a single impact, right? So we take, well, not a single impact, if we take a single element like this element here that crosses a crack that it opens, we can look as we solve this algorithm for each damage point, we can see this increase till about 50 impacts and then a relatively constant increase in resistance. And this actually lines up with what we saw from the experimental data and how that crack opened, right? So this crack starts to open from 0 to 50, then after that, the impacts of the plate really didn't do anything. However, like any machine learning algorithm, if we provide it with a better initial guess, we can get better results. So here's those exact same results, just in a different color map and flipped to look from the back. These were the SECs that we discussed before on the back of the plate. And so 20 SECs. From the SECs, we were able to, From the SECs, we were able to see individual cracks that form through particular SECs. When we take a crack that forms through an SEC and feed it into the algorithm, we get a much better result that now can start to track not only some of the damages, but some of this much smaller, not only some of the spalling, but the much smaller damage that happens along the crack lines, right? And this is provided by the fact that the initial guess means we're not just concentrating on the largest damage first, right? We're spreading out to where we know some more damage is. So kind of quickly here to recap what we did, we're trying to deliver actionable data for dense sensor networks, and we're developing the methodologies and technologies to get us there. The only 2 things we talked about today are really these 2 sensing technologies, but at the University of South Carolina, we're focusing much more on feature processing and prognostics. So some key developments, right? We implemented a highly scalable SEC-based dense sensor network, developed an incipient damage detection algorithm for the SEC-based dense sensor network, developed a deployable self-sensing cementitious material, and then devised a model-assisted damage detection technique for that material. So, thank you. I think Jim's coming up here, so
thank you, Austin. So we'll acknowledge you just a second there, but you have to answer the questions first. So if there's any questions from the audience, I'm sure there will be. There's a way to send those in, by chatting? And Tommy, our IT person, will receive those, and you could also, I guess, unmute and ask directly Austin a question, and then he'll try to answer that. So are there any questions so far? I have one that I'll ask.
Go with yours first.
I'm sorry, pardon?
Go with yours first.
Oh, so also I have a question about that covariance matrix at C. We've been doing some unscented common filtering aspects, and is that matrix always positive definite? Because you have to invert it. That's a matrix of covariances, uncertainty.
That's a very good question. I'm not going to open my mouth because I'm not sure on that one. So that matrix is a matrix that we're always building. I'm always seeing positive numbers in it. Whether it's mathematically always, I'd have to look into that more.
Okay.
So, but we have to build that, and that the parameters that we set, particularly the nugget and the power term in our power function, are going to give us our variances. And so it is something that we are working on developing an automated method to kind of tune that in with data from the SECs themselves. Because right now they are just, we're matching it up to the strain map data that we have.
Okay.
But it's not an automated.
Okay. I'll be interested to see what you find out there. Any questions someone wants to
Yeah,
ask?
we have a question.
I see like a blue hand.
Right, so you are unmuted. Whoever has that question on the line, I can't really read the name here. Your origin.
So you can just ask directly. You should be unmuted.
Yeah.
You want to ask your question?
Okay.
Yeah. We can't hear. So if you want to type in your question, okay, why don't you glue the sensors fully on the concrete when you monitor the cracks? What is the minimum crack size that can be detected?
Yes. So let's go back to that because that's actually an interesting question. This is probably the one that we're discussing. If we glue the sensors directly, completely under, right? So right now it's glued on the edges. If we glue it completely under, we're actually not monitoring the expansion of that joint. We're monitoring cracks in the glue. So when these cracks get quite big, sometimes you have a glue that will stick over a gap. And we were trying to get our nice, clean measurement signals. For smaller measurements, gluing it all the way across is definitely more advantageous because we'll start to get every small variation. But when you want nice, long, I don't know if you can see this.
Yeah, we can see this.
Okay, but when you want these nice, long, clean signals, that's more like an LVDT. Gluing it on the edges is a much more appropriate response. So for smaller cracks, we have found that gluing completely tends to help. For these larger cracks, gluing completely will get you lots of ripples that are just a function of the glue cracking and not so much of the actual expansion of the joint. And so it definitely needs some more investigation.
But do you know what is the minimum crack size that can be detected?
So we're doing fatigue cracks, right? The minimum crack size is not actually a function of the sensor, it's a function of the SEC itself. And I would have to get with the team from Kansas to get you a number, but it's fatigue crack size. We're not having any issue detecting fatigue cracks. So, but those are glued completely, the fatigue crack ones are.
And following up on that, regarding the fatigue application, is there a way to distinguish between big cracks that don't need repair and small cracks that do not need repair?
So a sensing technology is just going to give you information about the crack itself. That follow-up needs to be done in either some sort of like model updating scheme or with a qualified engineer or technician, just the same way that we monitor for fatigue cracks now in a structure, right? But you know, all structures have damage. It's how much you're willing to accept.
Any other questions?
That's all I have right now. I'll see if there are
Okay. Any questions from our audience that's actually here?
So if I have a crack already on the beam, then I place the sensor on it. Is it able to catch that crack?
Can you repeat the question?
Sure. So,
thanks.
yeah.
So my question is.
Oh, I was asking your name.
Have him repeat
Okay.
it, so because they may not be able to hear it on the microphone.
A question was asked that if you have a crack on the beam and you place the sensor on the crack, will you be able to detect the crack? Right. And so if you already have a crack on that beam and that crack is static and it's not growing, you won't see anything. But one of the issues that actually raises is where is that crack going to grow to? So if you have a fatigue crack that's growing and you try to, say, put a relatively short gauge length strain gauge on it, like a resistive strain gauge, that fatigue crack may grow around that. So in this situation, you can put a sensor on that's very large, and then as long as that fatigue crack grows in any direction, you'll be able to detect it. But you'll only be able to detect the changes after that point, which is why it's important to detect damage early on, right? Because detecting damage early on will allow us to look, gather that data, you know, for a prognostics type view looking forward. Am I calling on people?
Go ahead.
Sure. Okay.
It's a class.
So my question is, how do you differentiate the reading from the reading? Oh, sorry, the error come from the damage to the sensor itself and the damage from the structure. Because from the reading, for example, for this one you have a jump, but if you damage the SEC, you may also have a jump in the reading. So how do you differentiate that?
Correct. So you're probably looking at this, right? How do you know if this is damage to the SEC or damage to the structure? You would have to go out and look at your sensors, right? But that's simple. I mean, that's for anything, right? If I take a notch out of a fiber optic strand, you know, how do I know? Well, it probably wouldn't even last if I took a notch out of it. But it's a certain challenge. But the way to look at durability is that if something happens to your sensor, you can still use that sensor as long as you know what happened to it, or you have a new baseline, right? And also helps in an installation. It makes it easy to install because all you have to do is glue and pre-stretch. And if you don't get it exactly right, it doesn't matter because it's your baseline that you're measuring off of. Kind of along the same as the last question, right? You only start obtaining data from when you place a sensor on. You don't have any information about what happened before. Although that's the information we really want. So.
But those damage doesn't affect your result, right? You can still obtain the structural damage.
Yes. So like on these damages here, like at 40 seconds, if there was a fatigue crack that opened in between, right, we'd see a signal. You know, you're not going to be able to tell the difference between the two unless you know that there wasn't somebody out there cutting it. But you know, you can paint over these sensors. So we had a sensor that was deployed for 5 years on a bridge in Iowa. This bridge got painted, so they ripped down our data acquisition system, brought the sensor back into the lab, glued it onto a plate with the green DOT paint on the sensor, and it still works just fine. But that paint would definitely change the value of the sensor. So.
Any other questions at all?
No more online. You're good to close.
So I think there's no other questions at or here. If you have any questions, I think there's contact information. You're always welcome to contact us or Austin Downey at the University of South Carolina. So you can do that if you have any follow-up questions. And remind you, we'll have some other seminars coming up, usually an average maybe once a month. We'll post those, so keep your eyes open for email or through the Design Safe. And if no other questions, I'd like to thank Austin there for his wonderful presentation and join me in thanking him, and those of you that participated here, we thank you, and also remotely. And with that, we'll close the seminar. Yeah, thank you, Austin.